Adversarial Robustness Toolbox open source project in particular. So yeah, what I was planning to cover was to start with an overview of the different adversarial threats that apply to AI. So I will give a short demonstration of those, but then really spend the majority of this session on showing you the Adversarial Robustness Toolbox open source project that we created in this area, and yeah, show you a hands-on example of how this toolbox can be used to evaluate AI models under adversarial threats. And then, yeah, I'll also share with you some resources and materials that you could explore if you want to study this topic in a bit more depth, and conclude with that. So the premise that, yeah, that I think this presentation starts with, and I think that many of us believe in, is that AI has tremendous potential, or as Andrew Ng has put it, that AI is the new electricity, which I think to me always means three things. So kind of same like electricity, AI is going to be everywhere. Also same as electricity, we won't even notice when we're using it, but then again, same as electricity, we will notice when it's not there. And of course, there's a lot of hype around AI, but I think this chart, I like to show it because it shows really the substantial advancements that have been made over the past decade or so, where on the left-hand side, you see the error rates that modern neural networks achieve on an important image classification benchmark, where you can see that over the last 10 years, error rates have consistently gone down. Clearly, an inflection point was the introduction of large-scale neural networks. And nowadays, so modern neural network architectures achieve, or in some cases even outperform human performance on such tasks. And on the right-hand side, and that's even several years old, that was back then already in 2017, a modern AI model was able on ImageNet classification to clearly outperform humans and very accurately predict more than 20,000 different categories that could be shown within an image. So this is great news, and of course that yeah, opens and creates a lot of opportunities to apply AI in various industries and business contexts. But it's also been found that AI is surprisingly brittle, which can make it prone to yeah, weaknesses that an adversary could exploit. And I'd like to show you a quick interactive demonstration of that. And so that's, you can also try it out yourself. So what we see here is an image recognition classifier. So as input, we provide an image. So here, for example, it's the image of a mousetrap. And you can see there at the bottom of the page that the model correctly predicts, yes, this image does show a mousetrap, and it's very confident, so has kind of 100% confidence in its own prediction. But what an adversary now could do is, so that an adversary could apply an attack and create a modified version of the original image, which, and so I'm hovering over that image. Hopefully you can also see it via the Zoom, but otherwise you can also try it out on the website yourself. The modified version of the image looks to a human identical to the original one. There's a small difference, but it's imperceptible. what you can see is now that on this modified version of the image, the classifier now completely misclassifies the image and now thinks this image shows a scorpion. And when you increase the attack strength, a human would still not be able to notice the difference. But the classifier would actually become more and more confident that this image indeed shows a scorpion. And that is not kind of like a one-off artifact. This is kind of on any of these images that are shown here. For example, we can get this car wheel misclassified as a goldfish, the light bulb misclassified as a zebra, the cat misclassified as an ambulance, or the cup of coffee as a jellyfish. So this is something that that an attacker could mount on any really machine learning model, and that of course it's surprising. So how can it be that the machine learning model that normally behaves quite well and gives good accuracy on test data becomes so brittle to these kind of targeted perturbation of its inputs? And that's then motivates looking into security implications of this phenomenon. So let me go back to the slides. So one thing to notice, we've seen an example here on images, but it's important to note this is not just specific to image classifiers, but this applies to other types of input data as well. So here's for example, a short video sequence, which if we perturb in the right way only one single frame of this image, the video will be misclassified as a tennis swing, whereas the original input is classified as correctly classified as a basketball throw. This is actually one of the notebooks that we have in our open source toolbox, which really shows, and when you look at it, which guides you kind of step by step in mounting this attack. And we will look at one of these notebooks shortly in more detail and go through all the steps that are involved. So yeah, broadly speaking, one can think of 4 different threats to AI. So what we've just seen, so where the attacker perturbs the inputs to the machine learning models and corrupts the output of the machine learning model, thereby that's called an evasion attack. Other types of attack that can be applied are poisoning. So there the attacker will insert poisonous data sample into the training data. And then when the model is trained as a consequence, it may contain backdoors or other type of vulnerabilities that the attacker could exploit later on. An extraction attack, there the attacker will try by querying the model to steal some of its properties, and for example, create a replica of that model and steal the intellectual property that went into designing that model. And it's surprising with how few queries an attacker can do that. And the last threat, the inference attacks, there the attacker tries, and again, that's typically via querying the model in a smart way, the attacker tries to infer sensitive properties that were contained in the training data. So if your training data, for example, contain sensitive personal information, the attacker might be able to learn about those by querying the trained model. And so it's not difficult to imagine scenarios where any of these threats could become highly problematic. So it's been demonstrated, for instance, in a security setting, that these evasion types of attacks can be mounted to fool, for instance, CCTV surveillance, and to, for instance, make people or certain objects kind of disappear from CCTV automatically analyzed using AI. In autonomous vehicle setting, it's been shown that object recognition systems can be fooled, or image segmentation models could be fooled. the autonomous vehicle misclassifies traffic signs. Cybersecurity, so there more and more machine learning is used, for instance, to detect malware, to detect spam, or to detect network intrusions. And there an attacker might try to modify the malware such that it still has the malicious functionality, but such that it also evades a machine learning model that's in place to detect it. And lastly, you can also easily imagine in the financial sector, for example, fraud detection, that there's a big incentive for attackers to evade any machine learning models that are in place. And I think more broadly, so besides these very specific attacker objectives, this all risks to undermine generally people's trust in AI. So if you see a machine learning model that completely misclassifies images and clearly processes images very differently from how a human process images, you may put less trust into AI models in general. And of course, that could have serious consequences for the adoption and acceptance of AI in our society. And sometimes people ask me, okay, is this all just theoretical, or are such attacks actually happening? And the answer is yes. Those attacks, we do see evidence that such attacks already occur. So for instance, in the cybersecurity domain, there have been reports that attackers use these adversarial machine learning techniques to programmatically evade malware detection system, for instance. And there do exist now official vulnerability nodes that flag vulnerability of an antivirus software due to these weaknesses and this brittleness of AI that we saw in the example earlier. And so this is something, therefore, that we decided to tackle. And one initiative that we started is the development and the release of the Adversarial Robustness Toolbox. So what is this toolbox? It is a Python library which implements state-of-the-art attacks, defenses, and robustness metrics for machine learning models. It's available open source. I put some links here, and I'm happy to share those later as well, those resources. And what this library really does, if you look on the left-hand side, so there's this small snippet of code. So it allows users to first load the art modules that they need to perform their analysis, load their test data, then load their machine learning model, for instance, a Keras classifier, then wrap it in art so that the art attacks and defenses can be applied. And then the user can perform attacks, and the user can evaluate how robust or how vulnerable the given classifier is in light of such attacks, and then compute statistics over that and compare to baselines, and for instance, measure the effectiveness of certain defenses put in place. We originally started with support for the most popular deep learning frameworks like TensorFlow, MXNet, PyTorch, but then since then have also added support for more conventional machine learning frameworks like scikit-learn or XGBoost. Because these threats do not only apply to deep learning models, but also to conventional machine learning models. We released the toolbox in 2018 at RSA, so which is one of the largest security conferences. I should mention, so back then it started as an IBM open source project, but recently in June, IBM donated this library to the for together with some of the other IBM open source projects around trusted AI. So it is now an open source project under the Linux Foundation for AI. And what I would like to do next is to show you an end-to-end example in art, how this all works. So I will open the notebook that I think gives a good example of kind of how this works end-to-end. But maybe it's also a good point to quickly pause here and to see if anyone has any questions about what I've presented and talked through so far. So I can't see any questions in the chat. Don't have the Slack channel open in front of me right now here, so I would ask the other panelists to please let me know if there's any question at this point. Otherwise, I would continue with the presentation of the notebook and.
Yeah, so I'm going to monitor the questions. So for right now, I think in the chat, there are a couple of questions. I'm sure, are you able to click the chat to take a look? Not on Slack, just the room, the chat.
Oh, I see. Okay, so there's one question about if these are all evasion attacks. I think the example that I'm going to show right now is going to be an evasion attack. I think also the examples that I just mentioned a minute ago, kind of in security, cybersecurity, autonomous vehicles, etc. Those were indeed also all evasion attacks. But we do have support in art also for the other types of attacks, like data poisoning, so both attacks and baseline defenses, model extraction attacks, and also what we added in our most recent release, inference attacks. But today, and also the example that I'm going to show in a minute, that will be on an evasion attack example. Okay.
Okay, great. I think, yeah, that's one questions in the chat. Again, for the attendees, for the questions to speakers, please post in the Q&A instead. It's much easier to monitor and get answered. Thank you.
Okay. So what I'm going to show now is one of the notebooks that we have in our open source project. So if you clone the repository, then in the notebooks folder, you will see we have quite a few example notebooks which show how to use art on different types of models, on different types of data. There's actually also a poisoning example that we have here. But the example that I will show right now is on a image classification task, and it shows an evasion attack end-to-end. So the first thing that we'll do in this notebook is to load all the prerequisites. And yeah, there's nothing too exotic here. We are gonna, the notebook is gonna install and open ImageNet stubs, so which is gonna provide us with some example images that we can look in this and use in this example. The machine learning model that we're gonna look at is a Keras model. So it's one of the models that ship with Keras. It's a ResNet 50 architecture for image classification. And then the remaining dependencies, those are all from art. And I will talk about those as we get there. So the first thing that we're going to do in this example, so we are going to load example images. So this ImageNet stubs contains 16 example images that we can look at. The images all have a resolution of 224 times 224 pixels with 3 color channels. So the dimensionality is 224 times 224 times 3. And I should say that this data set is very widely used to benchmark state-of-the-art image recognition models. Here in this example, we're gonna look at one image in particular, which is this one. But you can run the notebooks and also try out exactly the same workflow with other input images. So the image that we look at here from now on is this one. So the image of a person riding a unicycle. Now what we want to do next, so we want to load the ResNet 50 classifier from Keras. So that's what we're doing here. So this is calling the Keras built-in function, and we'll load this model into memory. So this is one of the really a state-of-the-art models on this type of data and on this machine learning task. And so what we do now is we just load the image and apply the Keras model to the input image and look at the prediction produced by the model. And we can see that the Keras classifier, the ResNet 50 model, correctly classifies this image as a unicycle or monocycle. So that's good. That's what we kind of hoping for. The model correctly tells us what this image shows. What we will do next is we will create a art Keras classifier wrapper around that model. So this is what we're doing in the next cell. At the core, what this means is we're taking the Keras model, but now we're creating a wrapper around it, an art wrapper, so that from now on art can interface with this model without having to know whether this is actually a Keras model or PyTorch model, but art has access to all the properties of this model that it needs to mount attacks against this model. There's one technical detail. So we need to tell art how to exactly pre-process the image. So this is something that Keras would do in a built-in function. So here it's something that we need to tell art explicitly. But then from this point onwards, we can call the art classifier, same as we called the Keras, the raw or the bare Keras model before, and it will give, for instance, the same prediction. So the same prediction that we obtained by calling the bare Keras model, we now also obtain it via the art classifier. But we do have, and that's the key of having this art wrapper, we have the abstraction from the actual backend, like Keras in this case. What now the art classifier does, besides the predict functions, it exposes a few other functions that are used typically in adversarial attacks. And one of these functions is to look at gradients of the models. And in particular, what we're looking at here and plotting here is so-called loss gradients. So those loss gradients tell us in this image of a unicycle, if I was an attacker and I wanted to change the image and change the pixel in the image such that the Keras classifier changes its prediction, which are the pixels that I should target? So it shows us, which are the most sensitive input features that might help an attacker to alter out of the And if we compare this to the original image, these areas that have kind of result in more brighter values here are probably the ones that contain most information in the image about kind of where's the unicycle located. What we will do next is then exploit this information to mount an adversarial attack. So here in this example, we perform a projected gradient descent attack, which is one of the strongest existing attacks, and it's also the attack that's, I think, the most widely used by practitioners to check how robust or how vulnerable their models are against attacks in general. So what we do is we create this ART projected gradient descent attack. As an input, this attack takes the classifier that we're targeting here. There are a few kind of attack hyperparameters that we're specifying here. And finally, what we're mounting here is a untargeted attack. So therefore, what this attack will do, and that's by calling the generate function on this attack and providing it the original input. It takes the original input, it gives us and returns an adversarial output. When we call a prediction on this adversarial output, what we will see is that now the prediction is different. So before the model predicted this and classified this image as a unicycle, now this image is classified as a mountain bike, all-terrain bike, off-roader with a very high confidence. And now you could say that, okay, this is not too far off. The original image showed a unicycle. Now the classifier thinks that this is a mountain bike, which is still a bicycle. Okay, but what actually happened is since we mounted this attack to be an untargeted attack, the only thing that the attack tried to do was to change the classification, which in this case then resulted in a misclassification, which is not too far off, but nevertheless, strictly speaking, the attack was successful. But yeah, I think what's perhaps more interesting and more impressive is when we mount a targeted attack. So in a targeted attack, we can pick the class that we want the classifier to predict on the adversarial sample. So this data set, ImageNet, has 1,000 different classes that the classifiers have learned about on the training set. Mostly animals, few objects like the bicycle that we just saw. And now what we can do is we can pick any of these 1,000 target classes and then mount a targeted attack that results in a prediction of this particular target class. So here we pick the target class 100, and 100 is class 100 is a black swan. So now what we're doing is we want to mount an attack where the unicycle picture is modified such that the model predicts the image shows a black swan. So all we need to do is we change the attack configuration such that the attack is becoming a targeted attack now. And then when we call the attack generate function, besides giving it the original input, the original image, we also tell it which is the target class that it should aim to produce. I think you just saw, so it takes a few seconds for this attack to run. But afterwards, what we see is, and so this is the new image, the adversarial image, which for us to human is indistinguishable from the original unicycle picture, but which now indeed is misclassified by the model as a black swan, and yeah, with 100% confidence in that. Just to that the two images, the original image and the adversarial image, they do look for us, like for human, the same, but there is a small difference between those two. And this is kind of measured and then shown in this cell. So this image shows the kind of the difference pixel per pixel between the original and the adversarial image, and also compute some metrics of that distance. And I think most widely used metrics are different LP norms. So like, for instance, the L0 norm counts how many pixels have been altered in the adversarial image, or the L infinity norm. I think that one's also quite instructive. It says kind of what's the maximum kind of percentage disturbance of any pixel value in the picture. So this tells us no pixel value has been disturbed by more than, or perturbed by more than 2% when creating the adversarial input, and yeah, that's too small a difference for a human to perceive. I'll maybe pause here for a second just to see if there's any questions to this point. So I don't see anything in the general chat, and nor in the Q&A. So then, yeah, let me walk through the remainder of this notebook. Oh, hang on, I think there was just an encouragement from Tim to all the attendees. Yeah, please, yeah, let me know if anything here is unclear, if you have any questions, ideas, suggestions. Okay, here's, I cannot open the Q&A. So now maybe to the panelists, if you could maybe read out the questions in the Q&A. Okay, here I see this question in the general chat. How does the attacker know how have we trained our image recognition system? That's a great question. Here we assume that, yeah, the so-called white box threat model, so in which the attacker has complete knowledge and information about the machine learning model. So here the attacker can, yeah, completely exploit all the knowledge about the model architecture, the model weights. The attacker can compute, therefore, gradients on the model end-to-end and utilize all that information when mounting an attack. Now, there exist other scenarios and other threat models. So on the other side of the spectrum are so-called black box threat models, where the attacker really doesn't know anything about the model internals. So the attacker doesn't know how we trained it, what the architecture is, what the parameters are, but where it's still possible for attackers to mount attacks, typically in an iterative way by querying the models and kind of iteratively creating an adversarial input. And we could look at that briefly after this notebook. So we have some examples of those as well. But here in this example, the attacker has all the information about the model. One question, are there any papers which describe some of the art techniques in the, yes. So we have also a white paper about art, which is on arXiv, and there you have references to all the original papers proposing these techniques. Leave also within art, typically when in our implementations of different attacks, we include a link to the original paper which proposed those. And yeah, I cannot see the questions in the Q&A. So Bill, out some of those.
I can read you one if you want, or post it into the.
Yeah, that will be great.
I think you may have already answered this one, right? This is what you just talked about, whether the thing has to be known.
Exactly, yeah.
Yeah. And then can we have the question is, can we receive the code snippet or try on our own? I guess it's the notebook public.
It's public, yeah. It's an
Okay.
open source project.
Okay, and we find the link on the art homepage, or?
This one is yeah. If you go to the GitHub repo, and then there's the Adversarial Robustness Toolbox, and then there's the notebook subdirectory. So there's a bunch of notebooks that you can see, that you can walk through. The one that we're looking at right now is the one called Attack Defense ImageNet.
Great. Okay, let me go. Bunch more questions. Oh yeah, we're getting there now. Okay, let me start from the top.
Mm-hmm.
I'm just going to post them into the chat. That's okay.
Mm-hmm. Yeah, it's strange. I mean, I can see that Q&A that there are 11 messages posted, but seems while I'm in sharing mode, I cannot open it. Yeah.
Okay, no worries. So this is from Yefim. Asks, so this attack requires access to the model, or only the model only, or also the seed training data?
Mm-hmm. For these kind of attacks, no, there's no access to the seed or training data required. So only the trained models, the model weights is all the attacker needs.
Okay. And then another one from Yoel. Is the attack to the target possible because the model is known? I think this maybe is a similar question to before. I.e., if it was a new model, how would an attacker be able to apply a specific target?
Yeah, it's true that, yeah, the attacker has to know what the classes are that the model can output. So you would have to know, for example, in this ImageNet example, that there exists an output class like Black Swan in order to direct the model and direct the adversarial example in this direction. That's true. So that's context information that you have to have.
Okay. And one more here. This is from Stefano. You always need to know the model, or can you just guess what perturbations will be effective?
Mm-hmm. Yeah, that's a great question. One thing that's been shown is if you take one architecture, say for example an AlexNet, and you do an evasion attack on that model, chances are high that attack and that adversarial example will transfer to other type of architectures. And that's actually quite an effective black box attack strategy. So take a different model. Maybe you don't know what the model is in production that you want to attack, but you have your own local model that you train on a similar data set. Create an adversarial example on that one, and that can be a good guess of a perturbation that could be also effective on the target model.
Great, thank you. Yeah, let's just go down the list. There's a bunch more questions. So here's one from, I hope I'm pronouncing the name right, Ryoji, asking, this is open source libraries designed for image problems only, or can it be used for natural language processing and speech?
Mm-hmm. So it's, yeah, that's a great we started initially with, particularly with image classification tasks in mind, but ART is generally applicable basically to any model which takes numerical arrays as inputs. So for instance, it's applicable to video data. And there's a notebook that we have which demonstrates an end-to-end attack against video data. Same also for audio and speech classification. But even, yeah, we also have examples, and it's also applicable on more structured data sets. So even like a simple data set like the iris data set that's often used to demonstrate kind of conventional scikit-learn type of machine learning models. And also, while originally we started with support only for classification tasks, we recently extended ART to support other types of machine learning tasks, like object detection, for instance, automated speech recognition. So some sequence-to-sequence model is something that we're currently developing. Text, not quite yet. Text is challenging because it's really kind of discrete inputs. So there's no really kind of notion of gradients that you could compute with respect to kind of discrete letters or words that those models take as inputs. But it's something that we're also looking into. How could we have ART support models with discrete inputs in general?
Okay, thank you. Let's do one more, and then I think you had a few more things to show, right?
Yeah.
Yeah, let's do one more. This is from Sudesh, asking, can we isolate or quarantine adversarial content and retrain impacted models? Or can we roll back, recover to a model of a prior version for retraining?
Mm-hmm. I think this is a great question because, yeah, it starts, yeah, because it brings up kind of questions around defenses. So what can you do to defend against these kind of threats? Yeah, I think the most principled approach to defend against adversarial examples is to include adversarial examples during the model training. So that's a protocol called adversarial training, and that one gives substantial accuracy. It comes at a certain cost, as of course. So training becomes more expensive. There may also be some loss of accuracy on benign samples, but that is, I think, the most principled approach to defend against evasion attacks.
All right, thank you. Maybe you continue, and then we can see how much time we have left. There's a couple more questions.
Yeah. Then maybe I'll quickly wrap up with this notebook, and that's also then I think concludes my presentation pretty much. I will go through this quickly because this now shows and demonstrate also how defenses come into the picture. So one intuitive idea, a natural idea how to defend against evasion attacks on images is by doing some sort of signal processing on the inputs. And so here we apply an ART defense, which is called spatial smoothing, which is performing some, you can see that here, some blurring of the original of the input. So which is kind of like a low pass filter. And the hope is that this will kind of get rid of some of the adversarial signal that causes the misclassification. And as you can see here, this looks promising. I mean, at least in the first place, if we apply this low pass filtering to the original sample, I mean, it doesn't hurt. The classifier is still able to classify the original sample correctly as a unicycle. But then also when we provide the adversarial sample, so thanks to this smoothing approach, the smoothing gets rid of the adversarial signal. doesn't classify this as a black swan anymore. That is good news. The concern, and still from a security perspective, the caveat is that if the attacker knows that you've put this defense in place, and kind of in security, you always need to assume worst case. And so worst case, the attacker knows you're using this defense, then the attacker can create adversarial examples that bypass this defense. And you can do that in art by first creating a classifier which utilizes a certain defense, and then mount an attack against the classifier with this particular defense. So here we are mounting again an evasion attack, projected gradient descent attack against the defended classifier. And what we obtain then is an image. And this attack, we have to run it a bit longer because of the defense that's in place. But then at the end, we will obtain an adversarial sample that is misclassified as a black swan, and that's also able to evade this spatial smoothing defense. And so this is the notebook. I will just very quickly go back to the slides and go to my last slide, which provides some pointers and resources. And then we can spend the last few minutes on more questions. So this is just a little background on art, but in terms of resources, so please check out our GitHub repo. So you will find the notebook there that we just walked through and a number of other notebooks, documentation. So you can check out, read the docs. I did not include here the link to our white paper, but I could make that available as well later on. We have a public Slack channel. Here's the link to the demo that I showed initially, a blog with more information about one of our major releases last year. And then, of course, there's the bigger picture around trusted AI and the work that IBM Research is doing in the space, including robustness, but also including fairness, explainability that have been covered in some of the other sessions. That's all I had. So thank you for spending the time with me. And I'm happy to take more questions till the end of the session.
Great, thanks, Matthew, for the grand presentation. I see there are quite a few questions in the Q&A. Are they already been covered, or?
Not all of them. I picked out a few, like 5 or so, and marked them as answered. So the ones that are still there are still unanswered.
Okay, is Matthew, are you able to click the Q&A to see all of the questions?
He can't see. Yeah, he had an issue. He can't see the Q&A module for some reason. So we have to read it to him or post it into the chat. Yeah.
Oh,
actually,
okay.
now, since I stopped sharing now, I can see them now.
Yeah,
okay.
They should have showing have 7 questions. Maybe we can just quickly go through from the top. If one is already answered, we just dismiss it.
So I think at what threshold can a human eye see the significant difference? That's a great question. And I think this is to some extent still an open research question. So I showed these LP kind of metrics, like for example, L infinity norms are widely used to measure adversarial perturbations, but that does not really correspond to human perceptions. So I think that's still ongoing work to find the right metrics which capture human perception and kind of tell you how far could an attacker go to mount something imperceptible. Can you estimate what model is being used? I think, that's been, I think, perhaps partially answered. You could do that by querying the model. You could also think about mounting something like doing first an extraction attack, so where you steal or infer about the model that you're targeting, and then devise an evasion attack, a black box evasion attack in a smarter way. A link to the white paper. Yeah, I hope I'll check with the organizers what's the best way to share that. Can you explain what an L1 norm would correspond to? So L1 measures kind of like the total number of, or total amount of absolute perturbation. So if you sum up over all the pixels, how much you perturb them. The loss gradient plot shown earlier, does it suggest that the model has not been trained on enough unicycle examples? It's a standard model, so I would think that normally it's been trained sufficiently well, and I think qualitatively you would see something similar on other inputs as well. Is it known how many images with black swans were used to train the original model? I believe ImageNet, it's 1,000 images per class. Now, one thing is, I showed the example with the black swan target class, but if you run that notebook yourself, you should be able to do everything and pick your own target class, and it should work the same. I mean, these targeted attacks using a strong attack like PGD, they're really 100% successful. How is art making the model more robust? So we do support some of these pre-processing type of defenses that I showed, like spatial smoothing. We have modules also for adversarial training, which I mentioned a moment ago is regarded as the most principal approach to train robust models. So we have a few defense modules. And can you please post invitation link for IBM Art Slack? And again, yeah, I can check with the organizers what's the best way to share that link. Yeah, the one that I had on my last slide, normally if you go there, you don't need an extra invitation, but should be able to join the channel. I believe that's all the questions that
we have one more left. That one is being answered.
Okay. What telemetry do we have to detect a skew in the quality of your training data? Don't know if that applies or is specific to kind of adversarial robustness. So yeah, I don't have a answer to this kind of like from an adversarial robustness perspective. I think that's perhaps a more general question about training data quality evaluations.
And then one more, can you make the slides available?
Sure, yeah, I'm happy to share those.
Yes, that's great. I think that's all of the questions we have. Oh, we just one more coming.
If confidence levels of the model output suddenly drop, how can we find out how, why, as well as the data that caused it? And one answer from the adversarial examples perspective, and some people have tried, and so researchers have tried to build defenses which they try to exploit that on an adversarial example, the model may be less confident than they are on natural inputs. But actually it's turned out that that's not a viable defense because like there exist attacks which allow